And we are back in business. Over the course of the last couple of videos, you learned what Eigenstuff is. And now that you have a feel for that, the time has come to learn how to compute the Eigenstuff. And the way I want to do that in this video is to begin in the simplest case with 2x2 matrices, and we will learn the relevant ideas and vocabulary in that relatively simple context. Then we will jump up to 3x3 matrices, and looking at an example or two in that context will help us see what still works and what suddenly becomes harder, and that in turn will point us towards some of the difficulties that arise in the completely general case of n by n matrices. But enough introductory jibba-jabba. Let's get to work. Let A be a 2x2 matrix whose eigenstuff we wish to compute. The main thing we want are A's eigenvalues and the eigenvectors corresponding to those eigenvalues. In other words, we would like a description of the eigenspaces. And once we have those, we can decide whether we have enough linearly independent eigenvectors to form an eigenbasis. And if we do, we could go ahead and write an eigendecomposition for A if we want one. But everything really begins with the hunt for eigenvalues and the eigenvectors that correspond to them. So we want AV to be equal to lambda v for some scalar lambda and some non-zero vector v. And as we discussed a couple videos back, once we find a single eigenvector corresponding to a given eigenvalue, we know that more are about, and we'll then be able to go mining to uncover the entire vein of eigenvectors, the eigenspace corresponding to lambda. So for now, we just need one. Anyway, once we have stated carefully what we're looking for, we can begin down that path by taking some fairly natural algebraic steps. So here's our eigenvalue equation. AV is lambda v. And it's a funny sort of equation to solve because we are trying to solve not just for one thing in the equation, but for a pair of things, the lambda and the v. So it's not really just a matter of isolating one thing on one side of the equation. But with some cleverness, we can get this thing into a form that will help us. The first thing I want to do is to get an equivalence statement by pushing everything over to one side, like so. This gives us AV minus lambda v on the left and the zero vector on the right. Now at this point, it's tempting to try to factor a v from the left-hand side so that we will have the symbol v in only one place rather than two, which would certainly simplify matters. However, we can't just write the quantity a minus lambda times v is 0, which is why I have this in forbidden blood red symbols. You cannot do this. Why not? Well, look at the stuff in parentheses. What would that even mean? You can't subtract a scalar from a matrix. This is nonsense. But fear not, the idea was a good one and we can make it work. The only thing I can subtract from a matrix is another matrix of the same size. So we are going to be clever and find a way to do just that. Look at our original expression on the left. Even though it was a matrix times a vector minus a scalar times a vector, their difference is perfectly well defined because a matrix times a vector is a vector and a scalar times a vector is a vector. The problem only came when I tried to separate out the vector v. Well, maybe if there's a way I could rewrite the scalar times the vector as a matrix times a vector, then I could pull out the v and just be subtracting one matrix from another. Can I do that? Yes, we can, because, well, let me haul you off here into the Scratchwork dungeon. This works because for any scalar lambda and vector v, that product is the same as if I multiplied v on the left by the matrix lambda times the identity matrix. The proof is simple, and it will hold in any number of dimensions, not just for 2x2 matrices and vectors in R2. Let's look at this expression on the right, the matrix lambda I times the vector v. Well, the matrix lambda I will expand out as lambda times the identity matrix, which I've explicitly written out here. And the vector v, let's go ahead and write that as v1, v2, all the way down to vn. Now, we have a scalar times a matrix. We know how that works. You just scale every entry in the matrix. In this case, that would give us a new diagonal matrix, where the main diagonal has lambda on all of its entries, times our vector v. And as we talked about in the previous video, multiplying a diagonal matrix and a vector is especially easy. The result is that each component in the product is just the product of the components on the same row in the left. So here we get lambda v1, lambda v2, and all the way down to lambda vn. And if you don't remember that that's how it works in that kind of multiplication, Just work it out as you normally would, and you'll find you get this exactly. But what is this? Of course, each entry has a factor of lambda, so I can pull that scalar out, and lo and behold, we are staring at lambda times v. So we have found that scaling v by lambda is the same thing as multiplying v on the left by the diagonal matrix lambda I. And that makes perfect sense geometrically. Think about the action of lambda I. Think about it as a linear map. All it does is stretch every standard basis vector by a factor of lambda. So of course, what that map does is scale every vector by lambda. Anyway, with that taken care of once and for all, let's rewrite the left-hand side of this expression in our rewritten eigenvalue equation. Now we have it as AV minus lambda I times V is 0. And as silly as that little trick is, we use it all the time when we are computing eigenstuff. So much that you won't even think about it anymore after you've done it 2 or 3 times. But anyway, we did that here so that I can factor a V out of the left-hand side. Like so. This is perfectly legal because A and lambda I are both matrices. So this is a well-defined operation. We're just subtracting matrices of the same size, 2 by 2 in this case. But so far, I should mention, we haven't done anything that has required our matrices to be 2 by 2. We'll see soon why I'm concentrating on the 2 by 2 case though, for now. But so far, all of this is perfectly general. We'll be able to do this exact same analysis even when A is a 10,000 by 10,000 matrix. But let's take stock of where we are. We're looking for pairs, lambda and v, that satisfy this eigenvalue equation. Scalar lambda and a non-zero vector v. And we have such a pair that satisfies this equation if and only if this condition holds. If and only if the matrix A minus lambda I for some scalar lambda maps some non-zero vector v to 0. Well, hey, wait a second. That tells us something about this matrix A minus lambda I. If it maps a non-zero vector v to the 0 vector, then that matrix is implicated in some dimension crushing. Because if this matrix were a nice invertible matrix, well, of course, it wouldn't crush any dimensions. Its kernel would consist of the 0 vector alone. But since it's mapping some non-zero vector to the 0 vector, then its kernel is more than just the 0 vector. Its kernel is a space of at least one full dimension, maybe more. And that means however many dimensions are in the kernel, they are getting crushed, which in turn tells us something about the determinant of the matrix A minus lambda I. If this matrix causes some dimensional collapse, then its determinant must be 0 based on our work back in chapter 5, because the determinant, of course, is the n-dimensional volume magnification factor for the given matrix. But if the matrix crushes an entire dimension or more, then no n-dimensional volume survives the mapping. So the volume magnification factor would have to be 0. Good. Now we are getting somewhere. And notice what has happened in our last statement. The non-zero vector v does not appear. So we started out looking for these pairs, a scalar lambda and a non-zero vector v. And we said that's kind of a tricky thing to do, but we have rewritten it in this equivalent form where only lambda appears. That gives us high hopes that we can actually solve this thing for our one unknown, lambda. And once we know lambda, once we have found the eigenvalues, then we can take each individual value of lambda, each individual eigenvalue, substitute it back into our original expression, and then we will have an equation in which the only unknown is v, because we will know lambda. And then we can solve that for v and come up with the corresponding eigenvectors, the eigenspace that corresponds to lambda. Good, 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 good. The clouds are starting to clear, and we can see a path towards the solution of our eigenvalue problem. Now let's play around with this a little bit and get a feel for what it means in practice. And you know what? Since everything I've done so far holds for an n by n matrix, let's come back up here and change that, lest you forget that this analysis always holds. But when we do some concrete examples, let's begin there with 2 by 2 matrices. And in fact, to preserve some space, I'm going to collapse this all into its conclusion alone. Be sure you understood that argument, though, because in practice, that's the way we get from here to here, by thinking it through, which, once you're used to it, takes about 10 seconds, if that. Anyway, let's look at a concrete example. a 2 by 2 matrix whose rows are 2, 3, and -1, 6. And we want to find the eigenstuff of this matrix. So what we deduced above was that we have a magic pair, maybe we could call it an eigenpair, an eigenvalue lambda, and one of its corresponding eigenvectors, if and only if the determinant of this other matrix, A minus lambda times I, is 0. So we're looking for lambdas that will make a certain determinant equal to 0. And if we find such a lambda, then we know we have an eigenvalue. Well, let's look at our matrix A, and let's just compute some numerical examples. The determinant we're interested in is not the determinant of A itself. It's the determinant of A minus lambda I. So let's think about what that matrix looks like. Well, A, we know what that is. The rows are 2, 3, and -1, 6, minus lambda times I, where I is the 2 by 2 identity matrix. That looks like this matrix, a 2 by 2 diagonal matrix with lambdas on the main diagonal. And when we do that subtraction, we get this funny looking matrix. Let me go ahead and compress this. And again, this is one of those things that after you've done it twice, you will feel comfortable jumping from here to here in a matter of 2 or 3 seconds. But until you are comfortable, make sure you understand what is going on with that subtraction. You are subtracting off a diagonal matrix from A. Anyway, here is the matrix whose determinant we are interested in. We would like a value of lambda that makes this thing have a determinant of 0. Any such value of lambda would be an eigenvalue of our original matrix. The determinant of A minus lambda times I is, of course, the product of these two entries minus the product of these two entries, and therefore 2 minus lambda times 6 minus lambda minus -3. And we can simplify this into a quadratic polynomial in the unknown lambda. And the question for ourselves is, when is this expression equal to 0? Whichever values of lambda make this thing equal to 0, those will be our eigenvalues. Hey, that's a pretty neat polynomial. And in fact, we can go through this process with any matrix and come up with a polynomial whose roots are the eigenvalues of the matrix. This polynomial has a very special name because it's such a special object. It is called A's characteristic polynomial. I dislike this name, but we're stuck with it. I think a better name for it would be an eigenpolynomial. But don't call it that because nobody will know what you're talking about. But it just seems like such a natural name. After all, the characteristic polynomial is the polynomial whose roots are A's eigenvalues. So why not call it A's eigenpolynomial? I don't know, it's not up to me. You might remember 2 videos ago when I first introduced Eigenstuff, I mentioned that if you look it up in a German-English dictionary, one translation for the prefix eigen is indeed characteristic. So for whatever reason, we use that translation in this one case. So call it the characteristic polynomial in speech and writing when you're speaking with others, but bear in mind that we could just as easily call it an eigenpolynomial because that's what it is all about. The information that it carries is about the eigenvalues of a matrix. Those are the roots of our characteristic polynomial. Okay, enough grouching about terminology. For our given 2 by 2 matrix, we have found the characteristic polynomial. Its roots are A's eigenvalues. So let's find those roots. In this case, it's nice because this one factors into lambda minus 5 times lambda minus 3. It won't always factor nicely, of course, but the gods have always arranged matters so that in the first example you ever see of one, it factors so that you can concentrate on simple eigenvalues. Like here, what are the roots of our characteristic polynomial? Well, we can read it right off of this. 5 and 3. Those are the values that make this determinant equal to 0. So 5 and 3 are A's eigenvalues. Hooray! You have completed your first computations of eigenvalues. And now that we have A's eigenvalues, it's time to move on to the corresponding eigenvectors. In fact, let's find the eigenspaces, which contain all those eigenvectors for our 2 eigenvalues. I need some room, but I want to preserve this important equivalence, so I think this should do the job. Okay, so we have reached our first important conclusion. We found A's eigenvalues are 5 and 3. Next, let's find E5. That's my symbol for the eigenspace corresponding to the eigenvalue lambda equals 5. How are we going to do that? Well, I already hinted at it earlier. Once we know an eigenvalue, we can substitute that back into the original eigenvalue equation, and then the only unknown will be v, which stands for a corresponding eigenvector. And then we can solve that equation. So E5, that eigenspace, consists of all the solutions of the equation a times v is 5 times v, right? That's what it means to be an eigenvector of a corresponding to the eigenvalue 5. An eigenvector is one that gets scaled by 5. All right, well, this is easy because this is basically solving a system of linear equations. The only awkwardness here is that v, the thing we're trying to solve for, appears in 2 places. So we'll do the usual trick, push everything to one side so that we have av minus 5v is the 0 vector. Can I factor that v out of the left side? No, I can't, because then I'd be left with a minus 5, a matrix minus a scalar. Hey, we happen to know a trick for dealing with things just like this. Instead of 5 times v, we will write 5 times the identity matrix times v. And now I can factor that v out, and I will get a minus 5i. That's a perfectly good matrix times vector v is the 0 vector. Now v is in only one place. A minus 5i is a very specific matrix, namely this matrix when we subtract 5 off the entries on its main diagonal. So let's go ahead and rewrite this up here. For a minus 5i, well, let's see. Here's a. If I subtract 5 off the entries in the main diagonal, I get this matrix, whose rows are minus 3, 3, and minus 1, 1. For vector v, I'll just call that x and y, since those are our unknowns, and then equal to the 0 vector, which I could write out like this, 0, 0. And you know how to solve something like this. Let's begin by rewriting it as an augmented matrix, like so. And again, once you've done this 2 or 3 times, I promise you, you will end up going from here to here directly. But write it out once or twice, just to make sure you understand what's going on. There shouldn't be any mysteries here. To give myself a little space, let's clear this one out. All right, let's put this in reduced row echelon form. I'll leave those details to you. They're easy. But you should verify that when you do that, you end up with this. Well, we have that pivot right here, the 1, but in our second column, we see that y is going to be a free variable because that y column is a non-pivot column. And once we recognize that, we can go ahead and write down our solutions, where our solution vector xy will have the following form. Since y is a free variable, I'll just insert a parameter t, and then from the first row, thinking of the corresponding equation, we have x minus y is 0, or in other words, x is y, but I'm using the parameter t for y, so x is t. I can factor that parameter t out, and I have t times the vector 1, 1. So all scalar multiples of 1, 1 are eigenvectors of A with eigenvalue 5. Thus, E5, our eigenspace for 5, is simply the span of the vector 1, 1. So that means this matrix scales the vector 1, 1 by 5, which you could see very quickly if you multiplied A times 1, 1. You get the first column plus the second column, which is indeed 5, 5, which is 5 times 1, 1. But A also scales everything in the span of 1, 1 by 5. So it scales 42, 42 by 5, and it scales minus 7 by 5, so on and so forth. All right, well, what we did to find E5, we can do the exact same thing to find the eigenspace corresponding to our other eigenvalue, 3. So I'll just say, similarly, the magic word similarly, we can find that E3, the eigenspace corresponding to 3, turns out to be equal to the span of the vector 3, 1. And I will leave those computations to you. Do them. Pause the video here and do them. Okay, did you do them? Good. Well, now we have found the eigenvalues of our matrix and the corresponding eigenspaces. That means it is time for me to compress this work again. Okay, that is better. And now that I have freed up some space over here, let's think about these two eigenspaces geometrically. Let's start with E5. Well, it is the span of the vector 1, 1. Well, the vector 1, 1 looks like that, and its span, of course, consists of all the points on this line. Every vector on that line gets scaled by 5 when you hit it with matrix A. As for our other eigenspace, that is the span of 3, 1. Well, vector 3, 1 looks like that, and the span of that vector is the entire line on which it lies. Every vector on that line gets scaled by 3. So even though at first glance it's not really clear what matrix A does when it acts as a transformation, now we can see what it does. It really just amounts to 2 different stretches along 2 different axes, and everything else in the space just gets pulled along for the ride. Well, good. We have the core of our eigenstuff, but while we are here, we might as well observe that we have enough linearly independent vectors to write down an eigenbasis relative to our matrix A. So let's do that. An eigenbasis for R2 relative to A is, let's call it crazy B. We can say that it consists of the vectors 1, 1 and 3, 1. Now, it doesn't have to be those two particular vectors. We could take any non-zero vector from the eigenspace E5 and any non-zero vector from the eigenspace E3. So if we had, say, 5, 5 and 21, 7, they would still obviously form a basis for the space, and they're both eigenvectors, so it would be an eigenbasis. But obviously, we want to keep things as simple as possible, so let's just stick with these two vectors. And maybe for one last flourish, let's write down an eigendecomposition for A. Well, remember how this works. It's going to be the product of three matrices, and the general form of an eigendecomposition, as we discussed in the last video, was that our matrix A, provided that it admits a eigenbasis, as this one does, can be decomposed as V times capital lambda times the inverse of V, where the first matrix V stores an eigenbasis, the vectors of which are the columns of matrix V, and capital lambda is a diagonal matrix that stores the eigenvalues of A. But we already have all of that stuff, so we should be able to write down our eigendecomposition for A very easily. Matrix V is going to be the matrix whose columns are 1, 1 and 3, 1, the elements of our eigenbasis. If we had used different basis vectors for our eigenbasis, then of course we would have different columns here. Then comes matrix capital lambda. That, of course, is our diagonal matrix, the heart of any eigendecomposition, and its entries on the main diagonal are the eigenvalues corresponding to the respective eigenvectors. So the entry in the position 1, 1 is the eigenvalue corresponding to the eigenvector in the first column, which is going to be 5. And the entry in the 2, 2 position is the eigenvalue corresponding to the second column of matrix V. Well, that we know is going to be 3, and it's a diagonal matrix, so of course the other entries are zeros. And finally, we need V inverse. Well, that's just the inverse of V, and V is a 2 by 2 matrix, and such matrices are very easy to invert. When you invert this one, you get, as you should verify, this matrix, whose columns are -1/2, and 3/2, -1/2. And with that, we have successfully eigendecomposed, or if you like, diagonalized matrix A. Here are A's eigenvalues, and here are eigenvectors for A that make up an eigenbasis. Our original matrix A, which looked like this, and this diagonal matrix in the middle are similar matrices. They are two different representations of the same underlying linear map relative to different choices of basis, namely the standard basis, which gives us this original representation, or our eigenbasis, which gave us this much nicer representation of the same map. But I hope you will agree that this eigendecomposition is a very thorough X-ray of our original mysterious matrix A. All right then, let's jump up a dimension and find the eigenstuff of a 3 by 3 matrix. And as we do so, we will see what changes in the process and what stays the same. So how do we do it? Well, we're looking for eigenvalues and eigenvectors. So of course, we are going to begin with the basic eigenvalue equation. AV is lambda V, where lambda is some scalar and V is some non-zero vector. That's the equation that defines both eigenvalues and eigenvectors in the first place. So it's the obvious place to start. How do we begin to solve it? Push everything to the left-hand side so that we have AV minus lambda V is the zero vector. Now we would like to factor out a V, but we can't do that because it would leave us with a matrix minus a scalar, A minus lambda, which isn't defined. But you know the trick. Instead of lambda V, we can write lambda times the identity matrix, I times V. And now we can factor that V out because we're left with A minus lambda times the identity matrix, a matrix minus a matrix. Subtraction of matrices of the same dimension, of course, is defined. But now look at this equation we have. For this to hold, we have a matrix A minus lambda I mapping a non-zero vector V to the zero vector. Hey, wait a second. We know that the only way that a matrix can map a non-zero vector to the zero vector is if that matrix, or the transformation to which it corresponds, crushes at least one dimension. And that happens if and only if this matrix has a determinant of 0. And will you look at that? We have just re-derived this result that we boxed up earlier. And some of you might be thinking, well, since we came up with this earlier in the video, why did we rederive it? Why didn't we just call on this result and be done with it? Well, we could have done that, but I wanted to emphasize that it only takes about 10 seconds to think your way from the actual definition of eigenvalues and eigenvectors to this weird condition on the determinant of a strange matrix, which allows us to find the eigenvalues. And I think it's well worth your time to go through that 10-second mental operation when you're solving a problem like this. Because if instead of doing that, you just memorize this statement and without really understanding it, think to yourself, okay, I have to find eigenvalues. That means I need to write down this weird matrix, compute its determinant, and figure out where the resulting polynomial is equal to 0. Then all you've done is internalized an algorithm without actually understanding anything. If you go through that 10 seconds of thought, then you understand exactly where everything is coming from. So I encourage you to do just that. Anyway, what we have found is that we will be able to find at least the eigenvalues by setting the determinant of this weird matrix equal to 0. So let's do that now. The determinant of A minus lambda I is the determinant of the matrix we get by taking A and subtracting lambda from each of the entries on its main diagonal. Okay, so how do we get the determinant of this strange 3x3 matrix? Well, back in chapter 5, you had a homework problem. I believe it was number 18 in that chapter, in which you came up with a quick formula for computing 3x3 determinants. And you remember how it works. You end up with 6 terms, 3 that you add and 3 that you subtract. And the first one you add, you get by taking the first entry in the top row and multiplying it with all the other stuff on the main diagonal, so that we get the term 5 minus lambda times 1 minus lambda times 3 minus lambda. And to that we will add the product of 3 more entries. We start with the second entry on the top row and proceed parallel to the main diagonal, except when we exit the matrix, we come back on the other side like an old video game from the 80s. So we get 4 times 1 times 1. So I'm going to add their product, which is 4. Then I have to add a third term, which I get by taking the third entry from the top row and doing the same thing. I get 2 times minus 1 times 2, following that same direction. Well, that product is minus 4. Okay, but now I have to start subtracting things away. The first thing I will subtract is the product of the 3 entries I get by taking the first entry in the top row again, 5 minus lambda, and going down and to the left, so that I get 5 minus lambda times 1 times 2. So what I subtract off is 2 times 5 minus lambda. But I'm not done. I have to subtract off the product 4 times minus 1 times 3 minus lambda. So I'm subtracting off minus 4 times 3 minus lambda. And finally, I have to subtract 2 times 1 minus lambda times 1. In other words, I have to subtract off 2 times 1 minus lambda. Yuck! Well, before we set all this stuff equal to 0, let's try to clean it up a bit. This 4 and minus 4 cancel out, so let's bring this all together. And these last 3 terms, each one is linear in lambda, so let's go ahead and multiply that stuff out. And since this junk is all linear, we can probably do that in our heads. Let's see. Let's start with the lambda stuff. I'm going to get minus 2 times minus lambda, so I'm going to get a plus 2 lambda. Then I'm going to get, that's plus 4 times minus lambda, so that's minus 4 lambda. So 2 lambda minus 4 lambda is minus 2 lambda. Then I'm going to get minus 2 times minus lambda. That's 2 lambda. Oh, that's nice. That brings our minus 2 lambda up to 0. So there actually is no lambda left in all that. What about the constants? Well, we're going to get minus 2 times 5 is minus 10. 4 times 3 is 12. So that's going to give us plus 2. Oh, and then we get minus 2. So the constants turn into 0 as well. Interesting. So all this junk is equal to a big fat 0. That's very nice. Let's keep the rest of it in this form. If we multiplied this out, of course, we would get a cubic polynomial in lambda. But since the whole point is to figure out where this determinant is equal to 0, we can read it right off of this thing. Let's remind ourselves of a little vocabulary while we are here. This stuff, this expression, this polynomial whose roots are the eigenvalues of our matrix, matrix is called the characteristic polynomial of A. In fact, that's what this determinant gives us. This determinant, in general, is A's characteristic polynomial. And the characteristic polynomial is important precisely because its roots are A's eigenvalues, which is why I always want to call it A's eigenpolynomial. But since we have it nice and factored here, we can read off that A's eigenvalues are 5, 1, and 3. Those are the values that make the characteristic polynomial equal to 0. So that is the key to finding all the eigenstuff of this matrix. We've got the eigenvalues. And once we have those eigenvalues, we can feed them back into our eigenvalue equation, and then the only unknown in it will be the eigenvector, which means we can figure out the eigenspaces corresponding to each one of those values. Now that is a tedious task, so I'm not going to go through it all three cases here, but just as a quick reminder of one of them at least, we'll get started on the task. So next, we'll find the eigenspaces. To find E sub 5, the eigenspace corresponding to eigenvalue 5, we must solve, well, what must we solve? We are looking for vectors that satisfy this equation, AV equals 5V. But AV equals 5V is equivalent to AV minus 5V is the 0 vector, pushing everything over to the left. And I can rewrite the left side with the usual trick as A minus 5I times V is 0. And that's just a system of linear equations, right? That's our familiar AX equals B equation. And I know that I can solve that by looking at the augmented matrix to which it corresponds, where on the left of the bar, I have the matrix A minus 5I. So I just take A, subtract 5 from the entries on its main diagonal, and there you have it. And on the right-hand side of the bar, of course, I have the 0 vector, so just 3 zeros. And if you put that into reduced row echelon form, a task I will leave to you, you should end up with this stuff, from which we can read off the solutions very easily. We have our two pivot ones, and then we see that the third column is a non-pivot column, so it corresponds to a free variable. So if we think of the columns as representing x, y, and z, the components of the vectors that solve this equation, then since z is our free variable, we can go ahead and put a parameter, I'll use t, in that slot. And then we can read off what x and y will have to be. Thinking of the equation corresponding to the first row, that would be x minus 3z is 0. Or in other words, x is 3z. But we are thinking of z as t, so x is 3t. And similarly, on the second row, that corresponds to the equation y plus half z is 0. So y is minus half z. But we're using our parameter t in place of z, so this entry would be minus half t. And I could rewrite that as the scalar t times the vector 3 minus 1 half 1 for all possible values of t. So what we see is that E5, the eigenspace corresponding to eigenvalue 5, consists of all scalar multiples of the vector 3 minus a half 1. So we could say that E5 is the span of the set consisting of that one vector, 3 minus a half 1. But if I have some vector and I'm interested in its span, which is just the line it lies along, I could take any other vector on that line, and of course the span is exactly the same. So since we all dislike dealing with fractions, let's not use this vector. Let's use another vector on the same line. Let's just take 2 times this vector, and the span will stay the same. So if I double all those entries, they become 6 minus 1 and 2. And we have that first eigenspace. I have run out of space here, but of course you could go through the exact same types of calculations to come up with the eigenspaces corresponding to the eigenvalues 1 and 3. And if we do that, well, I'm going to need a little room here, so let me clean this up. That's better. So here's our eigenspace for the eigenvalue 5. But if we went through that same process, we would find that the eigenspace corresponding to the eigenvalue 3 would be the span of the vector minus 2, 1, 0, and the eigenspace corresponding to the eigenvalue 1 would be the span of 2 minus 3, 2. Since we had 3 distinct eigenvectors, and we are operating in R3, it's clear that each eigenspace had to be one-dimensional, because the sums of the dimensions of the eigenspaces clearly cannot exceed 3. It might be less than 3 or equal to 3, it just can't go over 3. I may have a little more to say about that towards the end of this video. But at any rate, what we've seen is that this matrix, the map that it represents, really comes down to stretches along 3 different axes with a different stretch factor along each one of those axes. That is not at all obvious when you look at the matrix itself. By the way, since we have our eigenspaces here, we can observe that we do have enough linearly independent eigenvectors to create an eigenbasis, which I'll call crazy B. And since these 3 vectors are linearly independent, they themselves constitute an eigenbasis for R3 relative to our matrix A. Again, we could have taken any scalar multiple of any one of those 3 and we'd still have an eigenbasis. And since we have an eigenbasis, we can diagonalize A, or stated in a slightly different manner, we can write down an eigendecomposition for matrix A. Let's go ahead and do that. An eigendecomposition of our original matrix A is that A is equal to, well, let's see, it's a product of 3 matrices, and we remember how it works. I'll remind you down here in the bottom. A is V capital lambda V inverse, where V stores an eigenbasis as its columns, capital lambda stores the corresponding eigenvalues, and V inverse is of course just the inverse of V. So let's write down A's eigendecomposition. The first matrix will be this one, whose columns are the eigenvectors in our eigenbasis, crazy B. Then we are going to get our diagonal matrix, whose diagonal entries are the eigenvalues. But remember, we have to take care to make sure that the eigenvalues match up with the appropriate eigenvectors. So since the first eigenvector in our matrix, V, is 6 minus 1, 2, which is an eigenvector with eigenvalue 5, then the first diagonal entry will be 5. Similarly, our second column in the V matrix is minus 2, 1, 0, which is an eigenvector with eigenvalue 3. So that means the second entry on the main diagonal will be 3. And of course, the last entry is going to be 1. We do have to make sure that those match up correctly. Otherwise, the eigendecomposition will not actually work. The product won't be equal to A. All right, this is a diagonal matrix, so all the other entries are zeros. And finally, the third matrix is the inverse of the first matrix. Ooh, who wants to invert that thing? It's easy enough to invert a 2x2 matrix, but inverting a 3x3 matrix is a bit of a pain. When I ask my computer to do it, it tells me that the inverse of this matrix is this horrid thing full of fractions. Well, I will take its word for it, and there is our eigendecomposition. All right, well, I'd like to make a few observations in passing about this first example we've done with a 3x3 matrix. Let's start at the end and work our way back up. Just a moment ago, we had to invert this 3x3 matrix to get our eigendecomposition. Now, inverting any matrix larger than 2x2 is a pain to do by hand. It's easy to do it, of course, but it is nobody's idea of fun. And just seeing this ugly matrix that came out as the inverse might make you think back to something from the previous chapter you read. In chapter 6, you learned that there's one very special kind of matrix that has a really simple inverse. Namely, if the matrix is an orthogonal matrix. Geometrically, that means it represents a linear isometry. Algebraically, that means that all its columns are mutually perpendicular and unit length. If we were so lucky as to have an orthogonal matrix in that position, then inverting it would be easy in the 3x3 case, or even in the 100x100 case, because the inverse of an orthogonal matrix is merely its transpose. But under what circumstances could we get an orthogonal matrix as that V matrix? Well, that would mean that its columns, which are the vectors in an eigenbasis, are mutually perpendicular and unit length. That would mean we could get an orthogonal matrix there if we had not only an eigenbasis, but an orthonormal eigenbasis. Wouldn't that be lovely? And when we have an orthonormal eigenbasis, which again just means a basis of eigenvectors that are mutually perpendicular and unit length, then our eigendecomposition would be that much easier to write down. And not only would we say that A has been diagonalized, as it has here, but we would say something even more rarefied. we would say that our matrix has been orthogonally diagonalized, which is that much nicer. It's like if you're playing poker, it's not just a straight, it's a straight flush. We love it when we can diagonalize a matrix, but if we can orthogonally diagonalize a matrix, so much the better. That's not going to be possible, for example, here, because although we can get an eigenbasis, these vectors simply are not mutually perpendicular, so we're out of luck. Anyway, we could say more on that topic, but I don't want to overwhelm you with it. Needless to say, it is important. And if you go on to study more linear algebra, you'll probably learn things like there are certain classes of matrices, most prominently real symmetric matrices, that are guaranteed to be orthogonally diagonalizable. But more on that in your second linear algebra course. Let's keep creeping backwards. Before we were able to think about the eigenspaces, we had to come up with the eigenvalues themselves. And those, of course, we found because we knew they were the roots of the characteristic polynomial. Now, in this particular case, for this particular matrix, the characteristic polynomial actually worked out very nicely, so that when we computed it and then simplified it a bit, it just fell into its factors very nicely. Well, that usually does not happen, and that fact has important consequences when we're trying to find eigenvalues. Let me show you a more typical example where the matrix hasn't been cooked up in such a way that everything works out nicely. So let's start over with a different 3x3 matrix. Here, the entries were not designed to have a nice characteristic polynomial. So this is a more typical example of what one might encounter in the wild. So let's say we want to think about its eigenstuff. Well, you're getting to be an old pro at this. You know, we're going to begin by looking for the eigenvalues. So there's the famous equation for finding them. And we can rewrite that in the usual way, doing the usual algebraic shenanigans. And we recognize that for a matrix to map a non-zero vector, as eigenvectors must be, to 0, we must have that the determinant of that matrix is 0. So let's compute that determinant. The determinant of that matrix, which is going to be our characteristic polynomial, is, that's going to be unpleasant to compute. Again, not hard, just unpleasant. And if we take the time to work it all out and then simplify the result, well, in this case, this stuff over here is not going to collapse into 0 like it so pleasantly did last time. Nope, here you'll get a linear expression in lambda, and over here you've got a cubic in lambda, and when you combine that all and do all the boring elementary algebra of multiplying this out and combining like terms, you end up with this cubic polynomial. Ugh. Well, that's our characteristic polynomial for A. Its roots will be A's eigenvalues. But what are the roots of this awful thing? When we have a 2x2 matrix, the characteristic polynomial is always a quadratic polynomial. And if we're lucky, that quadratic polynomial might factor nicely and we can just read off the roots. But even if we're not so lucky, we can always just find its roots using the quadratic formula. But now we've got a cubic polynomial as the characteristic polynomial whenever we look at a 3x3 matrix. Cubic polynomials are not nearly so nice. Does this one factor? Not in any obvious way. If you're a real elementary algebra master, you might know some obscure tricks like, what is it even called? The rational roots theorem, which gives you a hint as to what the roots might be if they happen to be rational numbers. But there's no reason to assume they would be rational numbers. But hardly anybody remembers what that theorem is, even if you've encountered it at some point in the past. And if you haven't, don't worry, you're not missing much. And even if you're familiar with it, it won't help you in this case. And you might wonder, well, is there something like the quadratic formula? Is there a cubic formula that gives me the roots of a cubic polynomial? In fact, there is such a thing, but almost nobody knows it, including most mathematicians, because it's quite complicated and it gives you the roots in a fairly nasty form. So we're not going to use that. Although I should mention while we're on that topic, even though there does exist such a thing as a cubic formula, which gives the exact roots of cubic polynomials, and there's an even more fearsomely complicated quartic formula for fourth degree polynomials, there is not a formula for fifth degree and higher polynomials, at least not one that gives you the roots in elementary terms. So if we were thinking about not 3x3 matrices, but say 5x5 matrices, where our characteristic polynomial would be not degree 3, but degree 5, we'd really be out of luck when we were looking for the roots. So we start running into serious problems with 3x3 matrices that become much more serious when we move up into still larger matrices. Anyway, what do we do with this thing? I've got the characteristic polynomial. I know its roots. are the eigenvalues of my matrix? How do I extract those roots from this thing? Honestly, in practice, you have to settle for approximations. Well, how do you approximate the roots of this thing? I mean, do you just graph it on a graphing program and look to see where this cubic crosses the x-axis? You could, and that would give you some crude approximations, or there are other ways to do it that are more sophisticated, but we're not going to get into that side of things. There is a whole field I think I have mentioned called numerical linear algebra, concerned with how one can do linear algebraic computations efficiently, and figuring out ways to approximate eigenvalues of large or even moderately sized matrices is one of the chief concerns of numerical linear algebra. Again, that's a topic for another course, but there's no reason why we can't mention it in passing here. As it turns out, this thing does have 3 roots, and therefore this matrix has 3 real eigenvalues, which I'll call lambda 1, lambda 2, and lambda 3, and their approximate values are minus 6.955, 3.217, and 12.739. Now, I am not going to use those values to go on to compute the eigenspaces of this matrix, although we might as well point out that since we have 3 different eigenvalues, and each eigenspace has to be at least dimension 1, and we're working in R3, we know that each eigenspace must actually have dimension exactly 1, because the sum of the dimensions of the eigenspace can't exceed the dimensions of the space in which we're working. So who knows, maybe I've got a line like this through the origin that is the eigenspace for our first eigenvalue, and it's going to be some other line through the origin that will be the eigenspace for the second eigenvalue, and there will be some third line through the origin that represents the eigenspace for the third eigenvalue. And if we take a vector from each eigenspace, they're going to be linearly independent, which means that we have enough linearly independent vectors to form an eigenbasis for R3 relative to A. That means we can diagonalize A. We can write down an eigendecomposition for A. And in fact, the middle matrix of that eigendecomposition will be a diagonal matrix, and the entries on its main diagonal will be these 3 eigenvalues. Again, I'm not going to bother with any details here, just thinking our way through it a little bit. The main thing I wanted to emphasize was the awkwardness of working with a cubic polynomial as our characteristic polynomial. There are other strange things that can happen in general, but I think it might be easiest for us to see in the case of a 3x3 matrix where the characteristic polynomial is cubic. I want to describe a few of those situations without even writing down specific matrices, because I think the computations can be distracting. And I want you just to think about the ideas in a mostly geometric setting where we can picture it in R3, though it will work in higher dimensions as well. And as I do that, I'll introduce some useful vocabulary associated with eigenvalues. So let's suppose we have some 3x3 matrix called A, and that its characteristic polynomial, which is necessarily going to be cubic if this is a 3x3 matrix, is lambda minus 3 squared times lambda plus 5. In that case, A's eigenvalues, the roots of the characteristic polynomial, must be 3 and minus 5. Now what's interesting here is that the first eigenvalue, 3, is a so-called double root of the characteristic polynomial, since the factor lambda minus 3 occurs twice. What, if anything, does this signify? Well, to get to the bottom of this, I'll need to introduce a little vocabulary associated with eigenvalues. The first term we'll need is algebraic multiplicity. This is quite straightforward. The algebraic multiplicity of an eigenvalue simply measures the number of times that eigenvalue shows up as a root in the characteristic polynomial. So in this case, since 3 is a double root, 3's algebraic multiplicity is 2. And similarly, since minus 5 only turns up once as a root, minus 5's algebraic multiplicity is 1. So far, so simple. Where this gets more interesting is with the notion of geometric multiplicity. The geometric multiplicity of an eigenvalue is the dimension of that eigenvalue's eigenspace. And this is something that we generally cannot tell from the characteristic polynomial. Sometimes we can, and we can do that because of one important result, which I will state without proof here, because the proof is fairly involved, but you should know it. The important result is that the geometric multiplicity of any eigenvalue is less than or equal to that eigenvalue's algebraic multiplicity. Sometimes that fact alone is enough to tell us what an eigenvalue's geometric multiplicity must be. For example, consider our eigenvalue -5. Its algebraic multiplicity is 1, so its geometric multiplicity can be no more than 1. That is, the eigenspace associated with -5 can be no more than one-dimensional. But of course, we also know that every eigenspace is at least one-dimensional. A zero-dimensional eigenspace doesn't even make any sense. The only zero-dimensional subspace consists of the zero vector alone, which isn't an eigenvector by definition. So anyway, we know that our eigenvalue -5 has a geometric multiplicity that is at least 1, but because of this inequality that I told you about here, we know that it's less than or equal to 1 as well. Well, if it's at least 1, but also no more than 1, it must be 1. Okay, simple enough. What about the geometric multiplicity of the eigenvalue 3? That's the dimension of the eigenspace associated with 3. Well, we know it's at least one-dimensional, but that goes without saying. That's true of every eigenspace. And according to this inequality, it's no more than two-dimensional. So that means the geometric multiplicity of 3 is either 1 or 2. And there's no way to tell which one it is from the characteristic polynomial itself. We have to go through the usual algebra to actually compute the eigenspace to figure out what that geometric multiplicity would be. That is, we would need to get our hands dirty and look at the equation AV is equal to 3V and go to work in the usual way. Push everything to the left, insert an identity matrix, factor out the V, set up the associated augmented matrix, row reduce, and read off the solutions. What those solutions look like will depend on what the row reduced version of this matrix looked like. For example, if our row reduction led us to, say, this matrix, 2 rows of zeros at the bottom, we'd know that our solutions would have the form x, y, z, and since we only have one pivot column here, our variables y and z are free variables, which means that we'll just give them parameter values t and s in our solutions, since they could take on any real value. But the top row in our augmented matrix in reduced row echelon form tells us, when we translate it back into an equation, that x is 2y plus z. Or in terms of those parameters, x is 2t plus s. And now we can decompose that vector into a linear combination of simpler vectors, so we could say that E3, our eigenspace, is simply the span of those two linearly independent vectors, which geometrically, of course, is a plane, a two-dimensional object. Aha! If this eigenspace is two-dimensional, that means that the geometric multiplicity of that eigenvalue must be 2. But again, there would be no way of knowing that without going through these sorts of computations. And the last thing I'll say about this example is that in terms of the geometry of the map, this eigenvalue of 3 with geometric multiplicity 2 means that the eigenspace for 3 is a plane through the origin, so every vector on that plane simply gets stretched by a factor of 3, whereas the eigenspace for the other eigenvalue, -5, since that eigenvalue has a geometric multiplicity of 1, is merely a line through the origin. Since we have 2 dimensions worth of eigenspace for 3 and 1 dimension's worth of eigenspace for -5, we have the ability to grab 3 linearly independent eigenvectors with respect to A. Something like this would do the trick. We just grab an eigenvector from E-5 and then any 2 linearly independent eigenvectors from E3. Those 3 eigenvectors constitute an eigenbasis for R3 relative to A, so we can diagonalize A. We could write down an eigendecomposition for A. Okay, I think you know all this, so let's consider a slightly different example. Suppose we had a different matrix, B, whose characteristic polynomial, let's say, is lambda minus 6 squared times lambda minus 8. Then B's eigenvalues would be 6 and 8 with respective algebraic multiplicities 2 and 1, just as we saw with our previous example. And once again, the geometric multiplicity of our eigenvalue whose algebraic multiplicity is 1 would have to be 1, thanks to this inequality. But when we look at our other eigenvalue, 6, which has an algebraic multiplicity of 2, the geometric multiplicity could be either 1 or 2. And it's entirely possible that when we run through an analysis similar to this one, we end up in a situation when we compute the eigenspace that we have only one free variable, and consequently, the eigenspace is the span of a single vector. It's a one-dimensional eigenspace, which means that our eigenvalue would have geometric multiplicity 1. How would that change things? Well, think geometrically what's going on. Our two eigenspaces both have dimension 1, so they'd look something like this. They'd be two lines through the origin of R3. So would we have enough linearly independent eigenvectors to form an eigenbasis for R3 relative to our matrix B? No, we would not. We could get two linearly independent eigenvectors, but that's not enough to form a basis for R3. So because matrix B has an eigenvalue whose geometric multiplicity is strictly less than its algebraic multiplicity, this matrix cannot be diagonalized. There is no eigendecomposition of matrix B. Let me show you a few more examples of the sorts of things that can happen. Let's consider a matrix C, another 3 by 3 matrix, whose characteristic polynomial, let's say, is lambda plus 1 times lambda squared plus 1. Again, this is a cubic polynomial, but there's something a little different here. It has an irreducible quadratic factor. There's no way to boil that down into linear factors, at least if we stick to the real number system. I'll come back to this point in a moment, but for now, let's keep it real. If we do that, then our 3 by 3 matrix C has only a single real eigenvalue, namely -1, which is a root of this factor. X squared plus 1 has no real roots, of course, because squaring any real number gives us something non-negative, and adding 1 to something non-negative clearly does not give us 0. Well, this root appears only one time in the characteristic polynomial, so its algebraic multiplicity is 1, and therefore, by the same reasoning we've used a few times now, its geometric multiplicity must also be 1. So now we're thinking about a map on R3 that has only a single eigenspace, and it is one-dimensional. Every vector in this space simply gets flipped over to its mirror image by the matrix C. Do I have enough linearly independent vectors to create an eigenbasis relative to C? No, obviously not. We only have one dimension's worth. We would need 3. So just like B, this matrix is not diagonalizable. Or as some people would say, it's a defective matrix. So no eigendecomposition for you, Mr. C. I did want to mention, though, even though we're not doing anything with complex numbers in this course, they do have plenty of uses in linear algebra. And we could take this characteristic polynomial and recognize that even though this second factor, lambda squared plus 1, doesn't have any real roots, it does have two complex roots. I, the square root of -1, and minus I. They are both roots of x squared plus 1, and therefore roots of the characteristic polynomial of C. And as a result, these are both complex eigenvalues of C. Obviously, they both still have algebraic multiplicity of 1, but once we go beyond that, things start getting very strange, so I will leave that for a more advanced course. We won't be working with complex numbers in this class, but you should know that if we wish to widen our horizons a bit, they definitely have their uses. And the last thing I will say is that even though we have been considering 3 by 3 matrices, this sort of language applies for all square matrices. All matrices, that is, for which we can talk about eigenstuff in the first place. Maybe as one last example, let's consider matrix M. Let's say it's an 8 by 8 matrix, and let's say its characteristic polynomial is this. Well, we can read off all the eigenvalues very easily. Those would be 0, 3, -4, and 7. And of course, we can see their algebraic multiplicities, which are 3, 2, 2, and 1, respectively. And for the sake of argument, let's just suppose that the geometric multiplicities of these eigenvalues are 3, 2, 1, and 1. So my question to you is this matrix M diagonalizable? Well, you should be able to see that the answer is no, because of this eigenvalue -4. That eigenvalue has a geometric multiplicity, 1, that is strictly less than its algebraic multiplicity, 2. And as a result, if we add up all the geometric multiplicities, we end up with 7. So we are one dimension short of the dimension of the space we are working with, which was R8. So there's no way to get enough linearly independent eigenvectors to form an eigenbasis for R8 relative to M. That means M cannot be diagonalized. There is no eigendecomposition for M. So sad. But you know what? Let's have a happy ending. Let's consider an alternate reality in which the matrix does have enough linearly independent eigenvectors to diagonalize it. Now the sum of the geometric multiplicities is 8. Yay! That means that it should be possible to take our matrix M and write it as V capital lambda V inverse. And if we wrote those matrices out, we would know what to expect. On the middle matrix, capital lambda, that's a diagonal matrix, and the entries on that main diagonal are the eigenvalues, and they get repeated according to their algebraic multiplicities. So for example, 0 is an eigenvalue with algebraic multiplicity 3. So that means the main diagonal will contain 3 zeros. And moreover, the first 3 columns of our V matrix, which stores eigenvectors, would all be eigenvectors with eigenvalue 0, and in fact, they would be an eigenbasis for E sub 0, the eigenspace corresponding to eigenvalue 0. And continuing along down the diagonal, we have eigenvalue 3 with algebraic multiplicity 2, so that would appear twice on the main diagonal. And in the first matrix, we would get 2 eigenvectors corresponding to 3, 2 linearly independent eigenvectors, that is, and they would constitute an eigenbasis for that eigenspace. And we have the same story with the remaining eigenvalues and vectors. And of course, all the rows of our first matrix V collectively give us an eigenbasis for all of R8 relative to our matrix M. All right, that's enough. My goodness, this was a long one. Be sure to do the exercises in the book where you will learn about, for example, the eigenvalues of triangular matrices and what is meant by the trace of a matrix. But enough already. Good night.